It's my great pleasure to introduce Campbell Harvey, the president of the American Finance Association, who's going to give the presidential address. It's been a real privilege to get to know Cam better these past couple of years working on the executive committee, to witness firsthand how deeply committed he is to advocating advancing scholarship in the field of finance and the diverse set of skills he brings to that important goal. Anyone who's heard Cam talk knows he's from Canada. His kids say that he claimed that he had to walk miles in blizzards to get to school. Cam, I hate to break it to you, but they went along with that thing for a while, but they're not buying the story. He migrated south to Chicago in 1983, earning his PhD from the University of Chicago in 1986. That's a PhD in just 3 years. I think the first inkling on Cam's vita of what we all know, that Cam is in a hurry to get things done. But he's been in no hurry to leave Duke, where he's taught for 30 years, and where he's the Paul Steek Professor of International Business. And it's fitting that Cam will be delivering his presidential address in Chicago, where he first got his start in finance. Cam started out doing work in consumption-based asset pricing, but from there moved on to what he's perhaps best known for, his work on international stock market integration, in a series of papers on his own with a variety of co-authors. He estimated the extent to which a stock market becomes more integrated into global capital markets when that integration occurs. And in a large body of related work, Cam also studied the determinants of stock and bond returns in emerging markets. Cam is one of a select group of people in our field whose work spans asset pricing and corporate finance. In corporate finance, he and John Graham had a radical idea. Rather than try to extract information on the determinants of corporate financing and investment from firms' observed behavior, they decided they would ask executives what drove their decisions. And it may come as a shock to this audience, but CFOs aren't listening to you. They don't think the cost of capital is project specific. They think of a firm's cost of capital, and they're willing to give up long-run economic value in exchange for higher short-term earnings. Cam's written many papers based on these surveys on a wide range of topics, including a recent paper on corporate culture. That's pretty far from consumption-based asset pricing that was in your thesis. I could go on, but it's going to be impossible to do justice to the vast number of papers that Cam has written. By my count, and it wasn't that careful, but it's at least this number, 129 published papers and 14 working papers. And it's remarkable how many papers he has with the same people. And I think that speaks volumes about the value other scholars place on working with Cam. And as one of the most highly cited financial economists of our time, he clearly has a strong following among other scholars. But Cam's contributions to finance have not just been through his own scholarly work. He is deeply committed to advancing finance scholarship more broadly. You know that he had a successful 6-year run at the Journal of Finance from 2006 to 2012. Many of you had your papers accepted by him with detailed comments, sometimes with an audio recording. More of you had your papers rejected by him. I know I did, but you still elected him, which is, I think, a good statement about what you think about his performance. His kids note that during his editorship of the JF, that it was a prominent part of their childhood, as Cam routinely edited papers on the sidelines of their soccer games. I hope you picked up your head sometime and at least acknowledged the occasional goal. And he's been an extraordinarily active member of the executive committee of the AFA, first as JF editor, then as vice president, president-elect, and president. During that time, he led efforts for the AFA to support the American Female Finance Committee, AFEC, now a standing committee of the AFA, the development of a code of professional conduct, a committee to oversee the Journal of Finance, renegotiation of the contract with the for the Journal of Finance, adoption of clearer procedures for the AFA nominating committee, enhancement of conflict disclosure at the Journal of Finance, upgrading the AFA website, development of a Journal of Finance mobile app. So many things, and recently has succeeded in enhancing the JF prizes and in working on collaborations with other professional finance-related organizations. I think all of this makes our field and our association much better. So, as part of the AFA tradition of gently roasting the president after all this praise, and Peter, I emphasize that these are supposed to be gentle roasts. I asked Cam's friends and family for some stories, and what they came back with were some pictures. So I don't have like a story. I have some stories that I've relayed, but I've got some pictures. And this was the first one that they sent. And then it came to me. Cam Harvey is actually a Jedi, a member of the Jedi Order, which I looked up, because I'm not a big Star Wars fan, but what I understand about the Jedi Order is that it mostly consists of polymaths. This is according to Wikipedia. These are teachers, philosophers, scientists, engineers, physicians, diplomats, warriors, and financial economists who all right, maybe not the financial, who value knowledge and wisdom above nationality. That's Cam. And it also says that by serving others, the Jedi give of themselves through acts of charity, citizenship, and volunteerism. That's Cam. And their traditional, it says also in the Wikipedia, go check it out, their traditional weapon is the lightsaber. That's the proof. He's a Jedi. Okay. But then I was scrolling through the photographs, and I came to this one. And my theory was shot down. Cam is not a Jedi. I do not think you can be a Jedi lightsaber. That can't have been a real lightsaber if you dress like that and you're into bird whistles. There are other pictures that help to reject the hypothesis, but to spare you the embarrassment, I will not show them. So while he's not a lightsaber-carrying Jedi, I think what is clear is that he has the other key attributes of a Jedi. He values knowledge and wisdom as evidenced by his extraordinary work as a scholar, and he gives of himself through the acts of charity, citizenship, and volunteerism as evidenced by his extraordinary contributions to our association. With that, let me turn it over to Cam Harvey, part Jedi president of the AFA.
Thank you, David. Let me just add one thing that Jim actually didn't mention in terms of the election. So you know the way that we do the election, there's only one candidate for president, and that was David. But there's also a place to write in a name. It turns out the second place was Donald J. Trump. So David, you beat Trump in terms of the presidency. Congratulations. So more seriously, it has been an honor to work with David in terms of all of the responsibility, the leadership, and the council, which I really, really appreciated throughout the year. Okay, so I've got a lot of thank yous to make, but very little time to do it. And I would like to thank my family first, my wife Susanna and children, Cassandra, Katrina, and Campbell, for all of the support that they've given me over the years. Susanna, Cassandra, and Campbell are here today, along with my sister and brother-in-law who came in from Toronto. It means a lot to me. And I see in the crowd many friends, many colleagues, many mentors. I owe also a lot of debt to my co-author Yan Liu, who read and commented very diligently on this address, about 30 versions of it. So thank you very much. So what I'm going to do today is maybe depart from the usual tradition. I've lost the team? Oh, okay. Well, I thought that was boycott. They know what I'm going to say. Okay, so I'm going to talk about the way that we do research today. So I guess I'm not going to talk about any of my research in particular, but I can't resist putting in a plug for some new unreleased research. So I've recently discovered a new factor. This is a great factor, a tremendous factor. It has about the same return as the overall market, but is uncorrelated with the market. Indeed, it's also uncorrelated with value, momentum, and size. Its performance is consistent through time, and the T statistic is huge. 3.23. I love this factor. I also love the uneducated. Okay, where's this coming from? I gave my RA instructions. Number one, form portfolios based upon the first, second, and third letter of a company's ticker symbol. Look at two samples, 1926 to present and 1963 to present. Try value weighting, then try equal weighting. Make a choice on delisting returns. Find me the best long-short portfolio based upon the maximum T statistic. So there are tens of thousands of choices of long-short portfolios. And it's no surprise that a long-short strategy has a significant T statistic. This is a brazen example of what I will refer to as P hacking. So you might think this is a silly example, but my address, which is on SSRN now, cites 3 different papers that focus on ticker symbols and claim to find excess returns. Many have interpreted my paper in the RFS last year as a call to raise the threshold for T statistics to something greater than 3. The point of our paper was that many in our profession, including me, were making a mistake in not adjusting thresholds for multiple tests. Today, I will attempt to make the case that making a decision based upon a singular threshold, such as T greater than 3, is not sufficient either. Multiple testing is only one issue. There are many other issues. Indeed, raising the threshold may have unintended consequences by increasing the amount of data mining. In addition, journals reinforce data mining by preferring to publish papers with the most significant results. Incentives may explain the publication bias on the editorial side. Journal editors are often competing for citation-based impact factors. Papers that do not report significant results generate fewer citations. Researchers also can induce publication bias. Authors might not bother to submit papers that they deem marginal. Authors might also file away an in-progress research project because they do not want to spend their valuable research time on a paper that they're not excited about. Here is some evidence of this effect amongst 314 factors published in top journals. Notice that the bar for the T statistic between 2 and 2.5 is about the same as 2.5 to 3. The blue line is what we would expect, and this is evidence of publication bias. So overall, we face a complex agency problem. Ideally, we want to quickly advance scientific knowledge in our field. Editors and journals publish papers with positive results. Authors believe a necessary condition for publication is obtaining a positive, significant result. Many time-intensive projects, for example, ones that might involve costly data collection, are not pursued because the risk is too high. However, I submit that these risky projects are exactly the type of initiatives that should be encouraged because they are often the ones that lead to a large advance in our knowledge. My address has multiple goals. First, it is essential to take a step back and examine how we do our research. Unfortunately, our standard testing methods are often ill-equipped to answer the questions that we pose. Other fields have thought deeply about testing, and I will share some of their insights. I will also advocate a simple Bayesian alternative that essentially involves a transformation of the usual p-value. Finally, I'll detail a list of best practices and offer some recommendations to both strengthen our research culture and encourage more research risk-taking. So journals tend to publish papers that report positive results or support the hypothesis that's being proposed. This is a statement about all scientific fields. However, there's considerable variation across fields. Notice that space science at the top has little problem in publishing articles that do not support the main hypothesis. At the bottom of the list is the field of psychology. Economics and business are not that far away from psychology. Perhaps more disturbing are the trends. This is the sort of situation that encourages p-hacking. So what do I mean by p-hacking? If you run thousands of correlations and report only the most significant, this is an egregious example of p-hacking. Such a practice, actually, is red flagged in the American Finance Association's Code of Professional Conduct and Ethics. However, there are much more subtle forms of p-hacking. For example, it might be that the author studied correlations amongst 11 variables and chose to report only 10 of the correlations. This is p-hacking, and unfortunately, not reporting all of the variables tried in empirical work is commonplace in financial economics. P-hacking can also occur when an author tries a number of different statistical approaches. For example, linear probability versus logit or probit, panel regression versus Fama-Macbeth, different clustering choices, different instrumental variables, and reports the one with the best significance. Indeed, researchers often convince themselves ex post that their choices were the ones that they had originally planned on. Data manipulation and exclusion are other p-hacking candidates. There are many choices that researchers make in terms of standardization, log or other transformations, Windsorization, outlier exclusion. If these choices lead to the most significant results being presented, this is p-hacking. The choice of data set is also a prime p-hacking tool. For example, if the researcher reports a significant result from, say, 1970 to present, and does not reveal that the same result is weaker on an extended sample from 1960 to 2016, this is p-hacking. P-hacking is more difficult to detect with proprietary data, where replication is costly. If a researcher is hand-collecting data on, say, 1,000 companies, does some analysis midway through the data collection, say at 500, finds a significant result, and stops the data collection, this is p-hacking. So with all of this talk of p-hacking, I think it's useful to take a step back and reflect upon what we are hacking. It turns out that the p-value itself is poorly understood. So the p-value tells us how likely it is we see an effect, or even a more extreme effect, conditional on the null hypothesis being true. And the null hypothesis usually no effect. However, p-values are often used in a different way. It is routine to look at a low p-value, like p equals 0.01, and conclude that there's only a 1% chance that the null is true, or that there's a 99% chance that the effect being studied is true. Both of these interpretations are incorrect. The p-value is the probability of observing the data conditional on the null. It's not the probability of the null conditional on the data. And unfortunately, these two quantities are routinely equalized. But it doesn't make any sense to equalize them. In my paper, I cite a colorful example. Suppose D equals death and H equals hanging. Conditional on finding somebody hanged, there is a very high probability that the person is dead, right? Say 99%. However, conditional on finding somebody who's dead, there's a very low probability, say 1%, that the person was hanged. Again, it is commonplace to mix up these interpretations, and this is not a small mistake. So there are many other issues with p-values. A p-value is routinely used to choose among specifications, but it's not designed to do that. A low p-value tells us very little about the ability of the model to explain the data. Think about a low p-value being associated with a model with a very low r-squared. Low p-values could be the result of failing to control for multiple testing, selection, model misspecification, and or p-hacking. P-values crucially depend upon the amount of data, and it's well known with enough data, you will get very, very low p-values. In addition, p-values do not tell us about the magnitude of the economic effect. Indeed, in 2016, as a result of a perceived crisis in conducting of statistical tests in science, the American Statistical Association published an extraordinary document called Statement on Statistical Significance and P-Values, which I discuss in my paper. P-hacking leads to a very high type 1 error rate. And essentially, the documented effects will not hold up at a sample. I do have some suggestions, but before we go there, I need to talk about another important force, the problem of rare or improbable incidence. So a rare incidence refers to an effect that is infrequent, like the diagnosis of a rare disease. An improbable effect is one that has limited or questionable scientific foundation. For example, a top journal in psychology recently published a paper providing significant evidence in support of extrasensory perception. So why is this an issue for the usual hypothesis testing framework? Let me illustrate this with an example from medical science. So for women between the age of 40 and 50, breast cancer is a relatively rare incident, impacting 1% of the population. The first-line test, a mammogram, is 90% accurate in diagnosing cancer. This is the power of the test, the probability of correctly rejecting the null hypothesis of no cancer. Assume the error rate is 10%, and suppose you are told that the test is positive. What is the probability that you have breast cancer? So let's work it out. Suppose we have 1,000 cases, and 10 or 1% have breast cancer, and the remaining 990 are healthy. For those with breast cancer, the rate of successful diagnosis is 90%, or 9 of 10 are correctly diagnosed as having breast cancer. For the 990 without breast cancer, 10% are incorrectly identified as having breast cancer. So that's 99. So we're left with 108. So 9 plus 99. 108 patients that are told that they're positive for cancer, but only 9 of these are correct. The rate of false diagnosis is 92%. The lesson here is if the effect is rare or improbable, the usual testing procedures will lead to a very high level of false positives. And we can see this mathematically. So let alpha be the error rate, beta be the power, and pi is the prior probability. Notice that even with 100% power, so beta equals 1, if pi is small, then the expected rate of false discoveries is very high. And with a very, very small pi, the expected fraction of false discoveries is close to 1. So one crucial addition here is the prior, which is easy to construct for cancer data, but not so obvious with many applications that we have in empirical finance. However, the prior is very important for our inference. Part of my mission today is to try to re-energize Bayesian thinking in empirical finance. There's a natural resistance to implementing Bayesian methods. Often the econometrics are challenging, computational requirements are substantial, and the approach is criticized for being too subjective because everybody's got their own prior. So let me motivate the use of prior beliefs with an example from a famous letter written by Leonard Savage to a colleague in 1962. He was trying to convince his colleague that priors had to be used in decision-making. He proposed 3 experiments. And these experiments involved a musicologist, a tea drinker, and a bar patron. So let's go through the experiments. So the first experiment, a musicologist claims to be able to distinguish between any pages of music written by Mozart or Haydn. You construct a test with 10 pairs of score pages, Mozart versus Haydn. And the musicologist gets every one correct. In the second experiment, an elderly lady claims that she can tell if the milk was put in the teacup before or after the hot tea was poured in. Again, you conduct an experiment with 10 different trials, and she gets every one correct. In the third experiment, a patron at a bar claims that alcohol helps him see the future. So you conduct an experiment at the bar, you flip a coin 10 times, and this drunk correctly guesses heads or tails for each flip. Okay, so for each of these experiments, the p-value is less than 0.001, which is highly significant by the usual standards. However, what you take away from these tests is different. In the first test, you already know the person's a musicologist. This is her expertise, and there's little reason for her to make a false claim. Indeed, it's not even obvious that you need to run the experiment. Nevertheless, the experiment confirms what you already believed. In the second case, maybe you were somewhat skeptical of the claim, but the evidence convinces you. Indeed, I remember that my grandfather would send tea back at a restaurant, much to the embarrassment of my sister and myself, because he always asked for the tea bag to be put in the pot first and then the water poured in next. And he knew if they got it wrong. So this experiment does change my beliefs. So what about the third experiment? The hypothesis is preposterous. Even though the p-value is less than 0.001, you chalk this up to luck. Your beliefs are largely unaffected. These simple examples drive home 3 insights. First, as emphasized before, if the effect is improbable, there will be a lot of false positives using the standard framework. Second, what really counts is the ability to change beliefs. Third, and most importantly, we need to use priors. So one of the reasons that the Bayesian approach is not widely used is that Bayesians have failed to embrace a simple alternative to the usual hypothesis testing method. I will advocate a simple compromise based upon a measure that's called the minimum Bayes factor. So let's start with the usual way of a Bayesian interpreting evidence. The posterior is simply the prior times the Bayes factor. The Bayes factor is the ratio of the data likelihood under the null to the data likelihood under the alternative. The Bayes factor tells us how much we are moved away from the prior given the evidence. A very small Bayes factor is supportive of the alternative. In general, the Bayes factor depends upon the prior specification of the alternative hypothesis, which can be very messy. But there's a special version of the Bayes factor called the minimum Bayes factor that does not. The minimum Bayes factor is the lower bound amongst all Bayes factors. It is achieved when the prior distribution of the alternative has all of its density at the maximum likelihood estimate of the data. In other words, it is the Bayes factor that provides the strongest evidence against the null hypothesis. So let me give an example. Suppose that you have 1,000 observations of returns. Your null is the average return is 0. Your prior odds are 3 to 7, which means that you believe the null is true with 30% probability. The average return, or the maximum likelihood estimate in the data, is 4%. Which prior specification of the alternative will deliver the maximum evidence against the null? It's obvious that setting 70% of the prior mass at 4% achieves this. What makes the minimum Bayes factor even more useful is that it's easy to calculate. It is a simple transformation of the t-statistic. And it's a t-stat of 2, which has a p-value of 0.05, corresponds to a minimum Bayes factor of 0.14. So let's use the minimum Bayes factor to calculate a Bayesianized p-value. So the Bayesianized p-value is the MBF times the prior odds divided by 1 plus the MBF times the prior odds. So if the prior odds are even, that simply reduces to the MBF divided by 1 plus the MBF. So notice that this p-value tells us the probability that the null is true given the data. The classical p-value cannot do that. The Bayesianized p-value answers the right question. So let me give another example. Suppose our null hypothesis is that variable y is not predictable by variable x. We run a regression, and the regression's got 300 observations and find a significant coefficient with a t-stat of 2.6. And the p-value associated with that is 0.014. The minimum Bayes factor derived from this particular alternative, so using that t-statistic, is 0.034. In addition, if we think there are even odds that the null is true relative to the alternative, this means that we can calculate a Bayesianized p-value, or the probability of the null, equals 3.3%. However, if you think there are modest odds against the effect being real, let's say 2 to 1 in favor of the null, then the Bayesianized p-value changes, and it increases to 6.4%. These Bayesianized p-values tell us the probability that the null is true given the data. This is exactly what we want and exactly what the traditional framework cannot do. In my paper, I detail another minimum Bayes factor, which is not so easy on the alternative. Here, our prior is centered on the null and is symmetric and descending around the null. And this seems like a reasonable assumption for many applications in financial economics. Again, the formula is a simple transformation of the usual p-value. There's no Wishart, there's no gamma distribution. This is really easy to calculate. In my paper, I suggest starting with even odds. This is the easiest and reduces to a simple transformation of the minimum Bayes factor. So, for example, in the usual testing framework, we usually think about a t-statistic being greater than 2 to achieve a 5% level of significance. Now, let's switch to the proposed Bayesian framework. With even odds, we need a t-statistic of 2.43 for there to be a 5% chance the null is true with the minimum Bayes factor. There's a number of insights here. First, and to repeat, we are now answering the right question. Second, to answer the right question, the thresholds increase with even odds. Third, the prior plays a crucial role. For example, if you believe the effect is only 20% likely, the threshold for the t-statistic increases to 2.94 for the MBF. Notice the threshold depends upon the prior. Of course, the solution that I'm proposing comes at some costs. Bayesian statisticians would always prefer the full-blown Bayesian approach. However, it is reassuring that the literature has shown, in particular a recent paper by Jim Berger in 2016, that the symmetric and descending minimum Bayes factor is very close to the actual Bayes factors when the minimum Bayes factors are very small. So my proposal is simple. For key hypotheses in your paper, along with the usual results, present a Bayesianized p-value with even odds. If the reader does not agree with your prior odds, the reader can apply a multiple to the Bayesianized p-value. In my paper, I provide some examples from finance, and let me go through them. So I divide my priors, so I'm imposing my prior on 3 different results for papers. The first study is the study of ticker symbols. And I put it in a group which I call a stretch. It reports a p-value of 0.008. So given that I consider the hypothesis a long shot, I'll calculate the minimum Bayes factor and use 99 to 1 odds. When you do that, the probability that the null is true is 74%. So this is a dramatically different inference than the traditional framework. The second study is the famous Fama and French 1992 size factor. The p-value is 1%. However, I label this as perhaps because there was no obvious economic foundation for the size effect in 1992. So with odds of 4 to 1, the probability that the null is true is 12.5%. So null being that size is not priced. The third example is the capital asset pricing model, which I consider on solid economic footing, a model built from first principles. With even odds, the probability that the null is true is only 3.5%. And again, where the null is that market beta is not priced. My recommendations fall into 2 categories. The first focuses on how we do our research. The second focuses on the incentives that exist in the publication process that impact our research culture and our field. So on research methods, spend time before looking at the data, establishing a research framework, which may include the economic foundation, the specific hypotheses to be tested, specification of data collection, including dates of the sample, all data exclusions, manipulations, and filters, the specific tests to be executed, statistical methods employed, table plans for results, and robustness checks. Such a framework ideally is transparent to other researchers. And there's a growing trend in other scientific fields, spearheaded by the Open Science Foundation, to post all these choices online before the experiment is conducted or data are collected. Number 2, checklists. Consolidated Standards and Reporting Trials, also known as CONSORT, provides a detailed checklist for researchers in medicine doing clinical trials. Each of the top journals in medicine has endorsed this checklist. I will endeavor to develop a similar checklist based upon some of the ideas in this paper. Number 3, statistical methods must take known problems like multiple testing into account. How many times have we seen a cascading table like the one on the screen? Various stars denoting significance. When multiple variables are tried, these stars are incorrect. Researchers should also be careful to focus on the magnitude of the effect, not just the level of significance. Code and data, when non-proprietary, should be shared, and shared in an easily accessible way. Papers should report all results, not just the selection of significant results. Internet appendices make this easy to do. If a result is surprising, it is ideal to try to replicate the result, perhaps on a new data set, before submitting for publication. Evidence is strengthened if additional tests of the main hypothesis are constructed, provided these tests are not highly correlated with the initial test. Priors should be taken into account. For example, an effect that is a result of a theoretical prediction should in general be treated differently than an effect that was discovered by some data mining exercise. That is, the economic plausibility must be part of the inference. Nevertheless, there can be theory hacking too, where various assumptions are tried to get a model to fit a known empirical phenomena. I'm reminded of Sandy Grossman's famous quip, "Theory is flexible." The most convincing theories have a new testable implication, and this is analogous to an out-of-sample test in empirical finance. And finally, alongside the usual test statistics, present a Bayesianized p-value. Our goal is to quickly advance knowledge in our field. In reality, researchers are rewarded for publication. Researchers know that journals publish papers with positive results. Indeed, editors, peer reviewers, and authors have incentives that are not necessarily compatible with our goal. We should care about discoveries, both positive and negative, that are repeatable in replication and in out-of-sample tests. In these replications, the initial finding is validated. In addition, we should not shy away from risky projects. It is a mistake to take the following message away today. Harvey advocates higher thresholds. It is more nuanced. The threshold should depend upon the economic plausibility. As I mentioned earlier, simply raising the bar to a singular threshold might lead to an increase in data mining. The adoption of a Bayesian approach should mitigate this problem because many purely data mined results suffer from a lack of economic foundation. As such, they will not pass the hurdle if prior beliefs are imposed. That is, much higher thresholds are necessary if the effect is improbable. I also believe that a consequence of the path that we've been on in our field is the proliferation of papers that are technically well executed, but that only advance our knowledge in a small way. Think of it this way. Suppose a researcher is choosing between two projects. One involves a year-long hand collection of data. The other one involves standard data like CompuStat. The researcher has even prior odds on the main hypothesis in both projects. The researchers know that it will be difficult to publish these papers if the result is negative. As a consequence, and this is especially true for junior researchers, the less risky project is often selected. However, it might be that risky project is the research that most advances our scientific knowledge. So what do we do about this? We need to select editors that will encourage more risk-taking. This means publishing some papers with results that are not positive. There are two motivations. First, a paper with a Bayesianized p-value of, let's say, 30% might be addressing an interesting economic question. Second, the effect might be true, and you don't want to commit a type 2 error. I used to worry about this a lot at the Journal of Finance. No editor wants to be the one known for rejecting the next Black-Scholes paper. In addition, top journals in financial economics should follow the lead of other fields and accept registered reports. These reports are detailed proposals that might involve the collection of new data, or it might be a proposal to do research in an unexplored field. The proposal is like a front end of the usual paper, providing the economic motivation as well as a plan detailing the statistical methods to be employed once the data are collected. The report is peer-reviewed. The editor makes a decision as to whether the research question is interesting enough to publish, even if the result is negative. There's also an understanding that it is inevitable that some choices will have to be made by the researchers that were not anticipated in the advanced document. These choices would be transparent in the final version of the paper. These actions effectively reduce the downside risk, and researchers should respond. There should be a greater cost associated with p-hacking. In our field, there are very few replication studies, and there are at least 3 reasons for that. First, there's a perception that given most of our data is easily available, there's no need to replicate. Second, journal editors know that replication studies are unlikely to collect as many citations and involve a lot of back and forth with the original authors. Third, researchers are not incented to carry out replication studies because they are not treated like regular papers in promotion and tenure decisions. The cost of replication needs to decrease. Currently, of the top 3 journals, only the Journal of Finance requires that computer code be submitted for the final version of the accepted paper. None of the top journals in finance require data. I would like to give a hat tip to a relatively new journal, Critical Finance Review, and its editor, Eva Welch, who has made considerable progress in making replication more mainstream. If there are more papers with negative results published, as well as replication studies routinely published in top journals, this inevitably means that the number of papers published in our top journals will have to increase. This is controversial, but technically feasible, given that the printed journal only has a few years left before going completely digital, and given that most top journals have gone to a multiple editor system. So let me conclude. We are a relatively young profession, and I believe the time is right to take a step back and think about how we do our research. The scientific outlook in financial economics crucially depends on our research and publication culture. Most importantly, we are not salespeople. We're scientists. How many papers include the language, quote, "this result is encouraging"? I'll tell you. Over the past 15 years, I counted 70 occurrences of phrases like this in our top 3 journals. This language is unscientific and reveals to the reader that the researcher has a particular agenda to find evidence in support of his or her hypothesis. This is the type of culture that motivates my paper. Most of us agree that the quality of research today in financial economics is very high. However, my paper is not about today. It's about tomorrow. We must avoid stumbling along the same path as some other fields. It is essential to build and maintain a robust scientific research culture. While there is some work to do, the scientific outlook in financial economics is very promising. My modest goal is to start a conversation about some of the issues that I've raised today. Thank you.
Thanks, Cam. To thank you for your work with the association, I want to give you this plaque. And also, as president of the AFA, you become a fellow of the American Finance Association, and I want to give you that. Thanks for everything you're doing. I do the adjourning? Okay. All right, well, I'm adjourning the meeting, but go next door. There's a reception just right next door. Look forward to seeing you there. Thanks, Cam, again.